Good evening and welcome everybody to Simplex Pachinko. This is Obi-Wan Pez. We are going to be doing some math tonight. Talking a little bit of shop with any of the educators that are out there. As it says in the description, I've kind of modified some stuff that we're going to be doing with my Calc 2 class this semester. Now granted, Calculus 2, they're probably a little more willing than usual. Some other groups of students may not be so willing to give stuff a shot, whatever, but we'll see how things go. So far, what I've done is I've basically taken... That's not plugged in. Man. It is a fairly regular occurrence on this channel that I do come in here and don't even bother to plug in the tablet, but it's still slightly embarrassing every time. There we go. So the method that I'm outlining here is mostly put forward by Peter Liljedahl in his book, Building Thinking Classrooms. And Sunil Singh in his book, Chasing Rabbits. I have mentioned both of these on the channel before, but you know. So mainly what I'm doing is I'm structuring my lessons such that there is 10 to 15 minutes of review. And this is probably going to involve a little bit of Q&A type stuff at the beginning of class. I'm trying to get away from, even though I got sucked into it this time, like explicitly going over, by the way, here's the like process as far as what you all should have learned last time. Right, so instead of doing process or procedure, in terms of review, I like to ask them, like, what exactly did they get out of it? What have students been working on? Since the last class. And I had a question this week, or today, in class of, towards the, or no, as one of our like warm-up exercises, I did this one. I think we did in stream here, I think, which was from Sunil Singh's book, The only real information we're given is that this is a midpoint here. And yeah, that's basically it. We're not even given any information that like this is a square. You kind of have to assume that it's going to be a square. Although I think as long as it's a parallelogram, this will still hold. So this is also something that is an interesting like thing to ask, is like, will this work for other shapes? Because if it's a general quadrilateral, I don't think it's going to happen. But you kind of have to find those bounds. But again, the point is that I'm not explicitly telling them that this is what needs to happen. It's just basically like, you know, what, when we get to the end of this, I'm gonna say like, what are we taking for granted? And one of the things that we're taking for granted is that this is a square. Not just that, you know, we're explicitly shown that the one diagonal is going through the midpoint on the top. But that's pretty much it. I gave the class vocal instructions on how to create this. So I said, you know, draw a square. Great. Draw well, I should have gone the other way, but I said draw one line that goes from a corner to the middle. Really? Took you that long, Stream Elements? That goes from the midpoint of one of your sides to an opposite corner. It doesn't actually matter which one, because as long as you get the right picture, it's basically just interchangeable with all the rest of it. And then draw a line from the one of the unused corners to its opposite side, or to its opposite corner. And so there's only really one way to construct this. As long as you have drawn it, drawn the two lines correctly, then it's going to either be a reflection or a rotation of the exact same thing that I did here. So, whatever. So there were a couple of false starts. People drawing like a straight up and down mid-line that goes through the square, making two rectangles. That wasn't really what we wanted. So, I told them this. And then the instruction was to find the area of the largest triangle. No other instructions. So we went over here, and if we assume that the side lengths of the squares are just 1, then the area of the largest triangle is a half. Because I completely forgot that, yeah, you could just literally draw right angle triangle here, and you get a half. So I said, okay, no, fair enough. There was only one group that did that. All the other groups decided that this was the largest triangle. So, you know, in terms of the subdivided triangles, yes, this is the largest. That's really what I meant. Find the largest triangle created by these individual subdivisions. Find the area of the largest one. So, that one right there. Alright, so I had a couple of different teams doing a few different options, like a few different methods to do this naturally. One of them was that they were trying to find the trigonometric values for all these things. So, naturally, first thing you want to do, go for a 45-degree angle, because this splits very nicely. Right, splits 45-degree angles here, 45-degree angles here. It does go across the diagonal, so in a square, that's exactly what's going to happen. All right, then I had a couple of people tell me that these were right angles. And therefore, because these are right angles, this should be a 45-degree angle too. And I said, fascinating. And a few of them kind of argued back and forth with a couple of the other people at their group before they went, oh. Yeah, no, that's not a 45-degree angle, and none of those in the middle are 90-degree angles. Because I said, like, okay, well, if it were 45, where would this connection be? They were like, they have to be over here, just like this one, going across the diagonal of the square. So, with that, didn't happen, but it was worth a shot. Okay, so then pretty much everybody tried trig at this point. I was kind of interested in the fact that they went so straight for trigonometry. Now, I will grant you that a number of them are, they're in Calc 2, so they've done trigonometry and they're kind of looking for a solution that's kind of proximal to where they are. So they're thinking to themselves, like, I need to find a solution that's going to involve math that I'm more used to. And so a number of them were thinking, trig, they're thinking calculus, they're thinking something around those levels. So sure, why not, right? These are both going to be 45, 45, 90 triangles to make the big ones here that cut this thing in half. So if those are 45, 45, 90, some of them were looking at like other angles in here and trying to figure out what they were going to be. Bertram, oh no. What you doing? If anybody else is in chat and has questions, feel free to let me know. Yeah, go for it. A number of them also went for this big triangle here. They could easily figure out the right triangle trigonometry that exists in this particular triangle. So of course they get a half here as the side length and a 1 there. Essential Calculus, 2nd edition, James Stewart. I don't know about Essential Calculus, but I do have a Stewart Calculus book. So I think my copy is probably at school. Yeah, I just have the multivariate one. So what's up? So yeah, a number of them were going for the trigonometry that they could create with this triangle being 1 here and a half there. They thought, well, we could figure out what the angles are. So here, from this one, we could do a tangent to get 1/2 over 1, or just the inverse tangent of a half, right? We'll get them this angle here, and the inverse tangent of 2, we get them this one here. So they said, aha, oh wait, hang on, let me copy this. Here's a 1. Nope. No, seriously, I just want to move. All right. And a 2. Okay. So group 1 said, all right, we're going to find this one here, but I'm going to find this one here by taking the inverse tangent of 1 over a half. Okay, so the inverse tangent of 2. All right, so we want this to be in degrees, and we want 2, and then we want the inverse tangent. 63.4349 degrees. Okay, and then over here, the inverse tangent of 1/2 over 1, so just inverse tangent of a half. So 0.5 inverse tan is 26, and naturally it's like the complementary angle to that one there. You still can't see when I point with that, okay? The complementary angle to 63.43 degrees, so this is going to be 26.56605. So it rounds up. This is always one of the fun parts of trig, when your three angles don't actually add up to exactly 180 degrees. It's off by that much. Right, so group 1 went with trig, and like this is almost everybody in the class. They're all in groups of 3, and they all pretty much all have independently decided or heard from other people that they're using trig. So naturally, yeah, sure, we'll use trig. Now again, this being a Calc 2 class, most of them are prone to thinking, and not necessarily just going to, copy off the group next to them or something like that. So, just make sure I'm not going to run over any chords here. So where do they go from here? Well, they also could either, some of them figured out that, oh look, I can make this into an altitude directly from this point here, which also gives me a 45, 45, 90 triangle here. If this is a half, then this is also a half. But wait. No, actually it wasn't. No, sorry. It was a half out to here. That's not it. As soon as I said it, I was like, no, wait. Right, so they want to know how much this portion is here out of this. They don't know. So let's get rid of that. Let's just move that up here. There we go. All right, I will be awaiting your email. Bated breath, I'm sure. Let me just see here. Yep, there we go. You're setting it to simplex, right? Nope. Yeah, that one. That one. Oh, okay. And anybody else who wants to follow along, feel free. What is it doing? Oh, there you go. Jeez. Yes, it is me. I'm literally in the same browser. Oh my god. Alright, whatever. Alright, whatever. It's hanging. Jerks. Alright. So with that, anyway. So these two are going to be the same size here and here. And then they said that this is going to be, some distance here. This is the same, and then therefore this is also going to be have some relationship. I forget exactly what they were saying, but a oh goody. Trig sub. So it looks like 1 over t cubed times the square root of t squared minus 1 from root 2 to 2 dt. Nah, that's pretty good. I mean, that pretty much sums up your mood right there, so. Okay. So then. So we're going to go over here. Go like this. I see, your two different variables are x and fancy x. Bold move. Alright, so I guess t is your original variable, but there isn't really. Flamelin, yes, we will attempt to explain some regression line stuff. Just a few minutes here. So, with this, you said, let's do. That's fun. Can you see that? No. Okay. The arrow like froze in place. It's very strange. Okay, so you said let t be equal to the secant of x, and therefore dt is going to be equal to the secant of x tangent of x dx. Okay, so I'll do. That's not what I wanted. Thank you. No. Root 2 to 2. 1 over. This is t equals these things. T cubed is secant cubed times square root secant squared x minus 1. Right? So this is really your key right here, is if you can see a function that will fulfill a Pythagorean identity easily, then that is perfect. So here what we want is one of these things that you're going to see this and you're going to go, ah, this is a Pythagorean theorem. Right, or rather this one right here. Ah, this is a Pythagorean theorem. T squared is going to be our hypotenuse. and then the 1 is going to be one of the legs. Again, it really doesn't matter which one you use, but yeah. All right, and then you can use theta to particularly talk about what these individually are going to be. Or you could use x in the case that you have here. I usually much prefer theta just because it's a little more obvious that it's not supposed to be something else. Okay, so here you've got this, and then you've got here our square root of t squared minus 1 is going to be the third leg. Because again, it's the square root of, this is c squared minus a squared, it's equal to b squared. But then you take the square root of both sides, you get b. So this is your second leg. So t squared minus 1. So here we want to know what the square root of t squared minus 1 is going to be. Well, the square root of t squared minus 1 itself can be either a cotangent, because here you're taking, there's a lot of different ways to do this. Alright, so anyway, one way is to look at this in terms of the Pythagorean identity, in which case you can just say, again, that your square root of t squared minus 1 divided by 1 is going to be a cotangent, or 1 over the square root of t squared minus 1 is going to be tangent. That's it. But then you got to figure out what t is. So t over 1 is going to be your hypotenuse over opposite. So that would be the inverse, multiplicative inverse of a sine function. So that's your cosecant. So if we were to do this purely from that particular stance, t over 1 would be a cosecant. Or then 1 over t would be sines. So if I went this way, following this one, I could let let 1 over t equal the sine of x, which then means that 1 over t cubed, which we have here, 1 over t cubed, is going to be equal to sine cubed of x. I'm doing something really far off the wall, by the way, in case you didn't notice. Okay, which also means that the square root of t squared minus 1, which is also over 1, under 1, is going to be equal to the opposite over adjacent, so that's your tangent of x. Yeah, regression lines can be a little bit nuts. So anyway, following the rest of this, you've got the integral as t goes from root 2 to 2 of the sine cubed x times tangent of x times, now you have to say what's dt. So if 1 over t is sine, then t is equal to the cosecant of x, which means that dt is going to be equal to negative cosecant x cotangent x, which also gets rid of some of this stuff. Dx. right? So the cotangent and the tangent are going to divide out nicely. The cosecant is going to divide out one of our signs nicely, and the negative just needs to sit out front. So this is going to be the not square root. The integral as t goes from root 2 to 2 of negative sine squared of x dx. So here you end up with the same stuff that we had before, right? You had it slightly differently, but it should work out the same either way you want to go. Okay, so if we go with root 2 over there, it's going to go that way. Root 1 goes this way. All right, so here, this is the same problem you had before, where you're stuck. So you can't do the integral of a cosine squared or a sine squared or anything like that, because here, if you try to split them up, you find that one of them is u, but then the other one isn't du, right? It's the same function, not the derivative function. So what's a guy to do, you know? Okay. Take that, bring it back. Okay. So over here, so there is a way, if you're doing just regular linear regression, there is a way to calculate all the parameters that you need. And it's not awful, question mark. If you want to do one with a like higher degree on it, then you're going to have a lot harder of a time. Your best bet is probably doing linear algebra. Yes. So for this, what you want to do is you say, hey, I remember some of those formulas we talked about in trig, which ended up doing the double angle formula and stuff like that. So the double angle formula, cosine of 2 theta is equal to 2 cosine squared of theta minus 1, or, and realistically, the one it comes from is cosine squared of theta minus sine squared of theta. If you don't like sines or cosines, exchange them for the other one, right? 1 minus that thing. Squared. All right, so then you could either do 2 cosine squared theta minus 1 or 1 minus 2 sine squared of theta. So take your pick, right? Which one do you want to do? In your case, you had the cosine of, oops, sorry. Right, you had the cosine squared, so you have to use this one. So you want the power reduction formula? Yep, just move it around. I prefer taking my cosine and swapping it. Oops, nope. I prefer moving the 1 here because you're trying to solve for the cosine of theta. So move the 1 over, it's 1 plus cosine of 2 theta, divide it, all divided by 2, then take the square root of all of it. Or, right, you're not doing that, sorry. That's the half angle identity. Use cosine squared theta. So cosine squared theta is equal to 1 plus cosine of 2 theta all over 2. Right? Yeah, this is all pre-calc stuff. And then here, same deal. This is the one that we need to use for this one, we've still got cosine of 2 theta over here. It's just now I would prefer to exchange our 2 sine squared of theta to the left and cosine 2 theta to the right, because the 1 minus can just stay where it is. So 1 minus cosine of 2 theta all over 2 again is going to be equal to the sine squared of theta. So it's the power reduction formulas are just the double angle identity. It's just traded around a little bit. Or the half angle identity without the square roots moved. So here, the one that I've got is going to be that we want, again, t is equal to square root of 2 to 2. Negative sine squared of x dx is going to be this thing again. So it's a negative 1/2 plus 1/2 cosine of 2 theta d theta. Oh, x and dx. Right, so then here again, you've just got your t equals root 2 to 2. Oh, nope. Right, we're actually doing the integral this time. So here, this is a negative 1/2 t. And then this stuff, we're taking the integral of a cosine. It's going to be positive. It's positive. We need a 2 dx as our derivative for the inside, so we don't have it. So now we need a multiply by 2 and also multiply by 1/2 again on the outside in order to make sure that these stay balanced. Yay. Gets crowded. Alright, so we get a 1/4 sine of 2x. And then 2 dx is absorbed into the whole u substitution thing. And that's going to be it. And then we have the evaluation of the integral. Man. That's an x. Sorry. Right, evaluated from t goes from root 2 to 2. So if t is going from root 2 to 2, we've got, for ours, t is equal to the cosecant of x. So x is going to go from root 2 for t is going to be the square root of 2 for cosecant. So when do we get the square root of 2? That's 45 degrees. So pi over 4. Right, and check me on that. But cosecant should be root 2 at pi over 4. Along with the secant, just about anything else. Yep, cool. And then we're going to 2. So a 2 for the cosecant is going to be 60 degrees or pi over 3. Nope, I'm wrong. It's pi over 6, isn't it? Right, because it's, when is the sine equal to 1/2? So yeah, pi over 6. Notice that these are backwards from how we're usually used to these things being. Right, they're in opposite numerical order. So we can either swap them in exchange for changing our signs, or we can just go through it as is. So that would be pi over 6 plugged in. So negative 1/2 times pi over 6 plus 1/4 sine of 2 times pi over 6. Okay, minus, which then becomes here, this is a negative 1/2 pi over 4, and plus 1/4 sine of 2 times pi over 4. Okay, so here this is going to be pi over 12, negative pi over 12, plus 1/4. This is the sine of twice pi over 6 is pi over 3. That's going to be root 3 over 2. Okay, here, this is going to be a minus a negative is going to be a positive. Half of 1/4 pi is going to be pi over 8. And then here, minus 1/4 sine of twice pi over 4 is going to be pi over 2. So the sine of pi over 2 is 1. Goodness. Worst. So yeah. Pi over 8 minus pi over 12. Simple arithmetic. All right, plus 1/4 parentheses root 3 over 2 minus 1. Fairly simple arithmetic in the second part. So this is going to be 3/24 minus 2/24 is going to be pi over 24. Okay, plus 1/4 root 3 over 2 minus 1. This is a negative value, but it should be small enough that it's not going to affect that. You know, you still should get a positive value, but we can see where that goes. Okay. So your root is going to look very much the same as this once you get down to there. Sorry, where are we going? Right, so in the one that I did, right, keep in mind that this is t is equal to cosecant of x. So we're saying that the square root of 2, root 2 is equal to cosecant of x, and specifically x is going to be on the first quadrant. So 0 to pi over 2. Right, it'll be slightly different. You should get the same values because you ended up with a cosine squared instead of a negative sine squared. So you're going to use the other power reduction formula and then take it that way. Right, so cosecant is going to be 1 over sine, so then the sine of x is going to be equal to 1 over root 2, right, which means that x is going to be pi over 4. We may come back to that, but all right, blend them. Woo. All right. M, your slope, is going to be given by n, the number of data points you have, times the sigma of the product of your x's and y's minus the sum of all of your x's times the sum of all your y's. Divided by n times the sum of all your x's squared minus the sum of all your x's all squared. So the sum of your x's all squared. Yes, the formula is a little weird. So all you're doing is you're taking all of your individual data points and it's trying to look at like so the sums of your individual terms and the sums of let's try this. The sums of your individual terms, as you can see here on the right, made into a product is going to be like if you did it out as a polynomial, right? This is going to be as long as your data list is, both for x and for y. So what does that do? Well, it means that all of your x's and y's are going to be multiplied together, going all the way down your list. But then that also means that you're going to sum up all of the other terms that you have, which is like x1 and y2, x1 and y3, x1 and y4, etc., x2 and y1, x2 and y3, etc., going all the way down. You skip the... I'm only skipping the one where it's like the same term, because those are already here, right? So keep in mind that those terms are going to be duplicated over here. The only difference is that they're also going to show up with this n multiplied out front. So it's essentially comparing, like, how good are all of your individual data points in terms of your slope here? How good are all of your individual data points compared to, like, the group of them? You can also drop the indices if you want and just have x's and y's. That's fine. I don't really care. But I do it for consistency's sake, right? So if you had a random set of data, come on, data. That's weird. I'm not doing that. That's what they mean. Okay. All right, I'm totally swiping this from somebody online. So the number of chimpanzees that go on a hunt out of a specific troop is given by the data set between 1 and 8. And the number of chimpanzees that go in a troop to go on a specific hunt to look for insects or forage or whatever they're doing, compared with the percentage of successful hunts. If just one goes by themselves, there's a 30% average success rate. If there are two, it's 45. If there are three, it's 51. 4 is 57. 5 is 60. 6 is 65. 7 is 70. And 8 is 71. So that is the information that we're given in terms of trying to find, whether or not there's a pattern in the data set. We'll find that out. So we want to know if the line of best fit is like even remotely decent. So this is how we find our slope. We're going to take all of this information. We're going to find all of our sums of x's, sums of y's, sums of the product, and sums of each individual thing squared, as well as the whole sum of all x's squared. So the sum of each x added up is going to be 1 plus 8 is 9 times 8 things that we have here is going to be 72, divided by 2 is 36. All right, that is a shortcut for adding up all of the integers from 1 to n, which is something else we did in class. Okay, so the sum of all y's here is going to be the sum of all of these individual numbers here, and I am not doing that in my head. It is 449. Okay. Then coming over here, we need to find the product. We need to find the product of each of these. So this is going to be xi, yi as a product. This is going to be 30, 90, 153, 228, 300, 36, 390, 490, and 56, 568. So over here we have the sum of xi, yi, which is the sum of all of those numbers added up, which 30, 90, 153, 228, 300, 390, 490, and 568. Cool. 2,249. Okay. And then we go over here and we say, what are x sub I squared and y sub I squared? You can do this pretty much anywhere you want. And then we want the sum of x sub I squared and the sum of y sub I squared. I'm none too concerned. I don't know if they're trying to look for, nuclear silos or what, but I will tell you that their spy satellites are probably having much better success. All right, y sub I squared is going to be 900. Oops. What's going on there? 45 squared is going to be 1625 plus 400. 16 is 2025. All right, 51 squared is going to be 2500, 2601. 57 squared is going to be 25. 3249. 3600, no brainer. 3625 plus 600 is going to be 4225. 70 squared is 4900. Again, zero effort there. 4901 plus 140. Yeah. 4901 is going to be 5041. Yeah, I mean, they're doing it just to, like, poke the bear, essentially. They're just, let's see how much we can piss people off. Just, I don't know. They're acting foolish, really, is what it comes down to. 26,541. Okay, so now we want to go and look at the formula based on these pieces of information, which, yes, there are quite a few. Okay, so our slope for this is going to be m equals, m equals n. We have 8 data points, so easy enough. 8 times the sum of xi, yi was 2,249 minus sum of x is 36, sum of y is 449, divided by n is 8 times x squared sum. I guess we didn't need to do y squared individually. Well, not yet anyway. Sum of x squared is 204. Minus sum of x squared is going to be 36 squared is going to be 936 plus 360. 936 plus 360 is 1296. Alright, so looking at this, we got 2249 times 8. Yes, I am going to do this by hand. Okay, so going across, we've got 72. 32 plus 7 is going to be 39. 16 plus 3 is 19. 16 plus 1 is 17. So 17,992 minus 449 times 36. This is where it gets fun. So in order to get the ones place, we're going to multiply ones by ones. So this is going to be 9 times 6 is 54. To get the tens place, we're going to multiply the tens by ones and the ones by tens. So in sort of an X pattern here, we've got 6 times 4 is 24, or rather 240. So we're just going to keep 24 in our head for now. Plus 9 times 3 is 27. So 27 plus 24 is going to be 51. Plus the 5 from the bottom is going to be 56. In order to get the hundreds place, we need to multiply tens by tens, hundreds by ones, and ones by hundreds. This hundreds place is a 0. So the 0 times the 9 is not going to give us any hundreds. So instead we got the 4 by 3, which is 12, and the 6 by 4. You still can't see me waving the... Man. All right, 4 by 3 is going to get us 12, and 6 by 4 is going to get us 24. So 24 and another 12 is 36, plus 5 is 41. To get the thousands place, we need to multiply the hundreds by the tens. So that's 4 times 3 is 12, plus 4 is 16. So 16,164. All divided by. This is going to be 1,632 minus 1296. Oops. Well, that was silly. Turned off my phone for no reason. Like a half hour ago. Alright, this is equal to 16,000 from 17,000 is going to be 1,000. And then 164 from 992 is going to be 828. So 1,828 divided by 1632 minus 1296. This is subtracting 1,300 is going to be 332, but then we need to add 4 more because we did not subtract 1,300. We subtracted 4 fewer than that. So 1332 plus 4 is going to be 1336. Okay, so our M is going to be that fraction, which if we find any common factors between 1828 and 1336, let's see, it's not divisible by 3. That's too bad. Okay, so y equals up here 1336 divided by x, and then we go to table set, start at 0. Oops. Okay, we got divisible by 2, clearly, both of them are. 4, both of them are. Divisible by 8. Okay, this is 1336. So is 1828 divisible by 8? 800, and no, it is not. So divide by 4 each. 1828 divided by 4 is going to get us 16 with 2 left over. Instead of 4. 2 left over is going to be 5 with 2 left over. 28 is going to be a 7. So 457 over. Divide this by 4. We end up with 3 with 1 left over from here. 13 again is 3. Divided by 4. Yeah, okay. With 1 left over, and then 16 makes it 4. So there you go. Our slope is 457 out of 334. Okay, y-intercept. B is equal to sum of y sub I minus m times sum of x sub I, all divided by n. Which is equal to sum of all y is 449 minus 457 over 334 multiplied by sum of x is 36, all divided by 8. All right. So this is going to be 334 449 minus 457 multiplied by 18, since 34 and 36 share a common factor of 2. You'll have 8,226 divided by 334 over 2 is going to be 167. All right. Cool. It's going to be 66,757 over 1,336, or thereabouts, to 49.9678. Okay. So it means for this particular data set with the chimpanzee hunting parties going out to raid for food and find bugs and cool stuff like that, we've got that y is equal to 457 over 334 times x plus 66,757 over 1,336. Hey, good job. Okay, so like I didn't finish this, right? No, I did. Never mind. Okay, so what they did was they translated back into t's, right? They came back to t's all the way. So they said, we're not going to be happy with just leaving it as x and then finding the values for the limits of integration. They're not going to do that, right? So they went all the way back to the beginning and said, well, if t is equal to, in your case, secant squared, then x is going to be equal to inverse secant of t. Yep. Right. So I actually generally, if I can find it, if it is an invertible function or invertible transformation, then I will go this route and say, all right, let's plug in the values into the new function rather than the composed function from the way back at the beginning. So you didn't have to, but it's an option. Yeah. Ooh. Yeah, no problem. Yep, so Blaine, this is going to be our line of best fit. And as you can see from the data, which you can totally see right here, you definitely can't see it. It's fine. All right, well, whatever. So this is, let's do Desmos calculator. So I'm gonna recreate the data table here. Okay, we'll do x-axis from -1 to 10, that's fine. Y-axis from 0 to 100, right? Because that's just percentage-wise. Sure, why not? Right, so we're going to go y equals 457 over 334x plus 66,757 over 1336. Gross. It's not even remotely correct. Great. Yeah. So something went wrong there. Let's look at that formula again. They got 5. How'd they get 5? Okay. Yeah, they got numbers that are just very different. Okay, so they plugged in 8 times 2,249 minus 36 times 449. What did I forget to do? Over 8 times 204 minus 36 squared. Okay, so 36 squared is 1296. Okay. And 8 times 204 is 1632. 1632 minus 1296 is 336. Oh. Yeah, no wonder. Well, that'd do it. All right. Damn it. All right, still divided by 4. So 336 divided by 4 is 84 instead of 334. So 457 over 84. Alright, same deal here. Can still divide by, in this case we can actually divide by 4. That's kind of nice. Okay, so 36 over 84 is equal to 3/7. Cool. Let's destroy that. Times 457. 1371 over 7. Okay, so 449 minus 1371 over 7, parentheses. That was not what I meant. All over 8. All right, there we go. 443 over 14. About 31.6429. Is that what they got? Whoa. Yep. 457 over 84 is about 5.4405. Cool. All right, we got it now. So 457 over 84 plus 443 over 14. Alrighty. Right, so let's actually show that one off. 457 over 84. Looks better already. 8 divide 443 over 14. Right. So that's our line of best fit. That's the best we can do, which is not great, but again, this is minimizing the amount of error that exists between all points. So you take all points, you sum up the square of their distances from the points individually to the line. So take those distances, square them all, and then add them together. It's called a least squares regression for that reason. It's going to find the place that you can fit this line which will minimize that distance. And it's squared so that one, sign doesn't matter. Positive and a negative are always going to end up being bad in terms of it is some distance away. If it didn't actually go through that particular point, it's going to count against it. And also, since this is curved this way, I think this should be a higher degree, at the very least polynomial, but we'll see how it goes. If you want to verify this, you can also do y1 is approximately equal to, use a tilde. All right. a times x1 plus b. And now we can get here, a and b are going to be the exact same values we had. So a is 5.44048, which is the slope, and b is 31.6429, which is also our y-intercept. The way that this is moving, what if this were a logistic, or not logistic, logarithmic? Oops. Right, so if we have a logarithmic curve that goes like this, we can have an r squared value, which is going to be based on how good of a fit this curve fits the data. We get an r squared value of 0.9941, which compares with the r squared value from the linear of 0.9271. So neither of these are really terrible. It's just a matter of not being able to more precisely fit the graph. Naturally, if we just get higher degree polynomials, we're going to eventually go through these points, but at the same time, like, complexity can be sacrificed for reasonable accuracy and simplicity of the algorithm that we're using in particular. So this is how we're going to do linear regressions for all of our stuff in our classes. You may or may not have it. But took up half a page. Oh, you just wait. All right, I'm going to run a 1 minute ad break. I'm going to go grab some water. So be right back, because otherwise I'm done with my coffee. So it's I got no liquid left. All right, see you in a minute. All right, we're back. So, one of the other benefits to running an ad break every so often is that this will also turn off the pre-roll ads for anybody new coming in for the next 20 minutes. So, well, I mean, the graph itself is not that bad. Oh, you probably can't see that. Let's go like this. I can totally, yeah, there we go. So now that I've bumped it up here, right, I'm just doing function transformations. This is stuff that I teach my pre-calc students, all the time. Make sure that you know how to do this basic stuff. Doing a logarithmic regression in this particular case allows us to get something that's at least reasonably accurate, right? That there's just like this one point, maybe this one here, that are a bit off, but all the rest of the points are fairly accurate in terms of how this fits. Logarithmic also makes sense in terms of, like, if you were to try to figure out why it is that a logarithmic function would determine like how much food the chimpanzees could bring back or whatever. So you'd need exponentially more chimpanzees in order to get like the next one amount of food. Because the more chimpanzees you bring, the harder it is for all of them to find like the same amount of food. They'd average to they would get a higher amount total, but they would probably average to a lower amount each individually bringing it back. Anyway. And again, we could try to figure out like what individually this all means in terms of like the individual values that we're looking for, A, B, C, and D. What do they mean in terms of all this? Yeah, we could figure out all sorts of stuff. Our B here is a really, really small number, which means that it has expanded. This has expanded our graph in the x direction quite a large amount. Which also means that D, the amount it's shifted up, is a large amount because it's going to take 188% in order to get out to our like standard values. Because again, we've expanded B so large. There is the possibility that we could manually change B and be like, nah, I just want B to be like 5, and then see what happens. In fact, with B equaling 5, we still get a our squared value of 0.9941. It did the same there too. It changes the B that's in the linear function. That's why this is all messing up. Just mute that for a minute. Right, so our best fit here is going to be these values. And if we just try to like fit any particular values in, then our D value on the logarithmic one will change. So if we get rid of this, yeah, see, our B now is 1, and D is 28.3582. So if we just let B be 1, then we get a D value of 28. So this is one of the other things, right? If we've got a multiplier on the inside of a logarithmic function, it's the same as having something adding on the outside. Another log adding on the outside. Right, we can split up those logs. All right, what else we got? What other questions do people have? All right. So let's go back to what we had back here. Oops. So we're trying to find the area of this black area here, this black triangle. Again, I had one group that was working out, trying to get by trig what the area of that triangle was. So they know the height, excuse me, they're trying to find the height here, and we had one group that was then trying to figure out, let's see, they said this one here. This group here is going to be the same as this one here. So this is going to be the inverse tangent of 1/2, which again is equal to 26.5650 degrees. Then they said because of this, we can do law of sines. We know that the sum of these two small angles is going to be 45 plus 26.5650, etc. And for that, what we then want to figure out is like either of the other two side lengths. If we just do 45 here, then we'll get this one there. Or if we do this one here, we'll get that one there. So the tricky part is trying to find like the known values. So law of sines. This was 45 plus 26 is 71.5650, etc. Taking the sine of this, and that's going to give us a half right under here, this whole side. And then let's do this one here. So this is going to be equal to sine of 63.4349 divided by here we can label this D, just because. D is equal to, exchange those, move the 1/2 at the top. So this is 1/2. Come on. Ratio between the sine of 63.4349 divided by the sine of 71.5650. Oops. Sine of 63.349. Realistically, you should use all available decimal places. Divided by sine of 71.650. So our D value here is 0.471404. Alright, and again, give or take, this isn't exactly going to work out 100%, but it's pretty close. So that's our D, the diagonal length here, which again is now going to be part of this 45, 45, 90. So we can divide this by D over square root of 2 is equal to the height of the small triangle, H sub S. So we're going to take that and we're going to divide by square root of 2. Well, that's convenient. We got 1/3. This is actually the answer I got, but I think I stopped here instead of actually solving the problem. Go figure. So h sub s is 1/3, which means that this height here right is going to be 2/3. That's probably not a good idea to do. Letters that are so close together. Alright, height, long, I guess. It's a terrible idea. It's fine. So if the long height is 2/3, and then the height going across, or the distance going across is 1, this is going to be 1/2 base times height. So our base is 1, our height's 2/3, half of that is going to be 1/3. So the area of this thing is 1/3. That's it. So I find this really elegant. RB Killa. Killa, yeah. Welcome in. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are discussing some math tonight. So, Peter Liljedahl is a Canadian, and thank you for the follow. Peter Liljedahl is a Canadian mathematician and teacher who has been working on building thinking classrooms. That's the name of his book, and also the name of his just overall project. The idea is that a lot of students have decided to kind of check out because lessons just really aren't all that interesting, and quite frankly, I don't blame them. I did too. Sunil Singh is a Canadian mathematician from the University of Toronto originally. He also did a lot of work in the public schools and also came to a similar conclusion. I went to the American Mathematical Association of Two-Year Colleges annual conference this year in Toronto, and just had a really inspiring and awesome time. So I highly recommend, if you have a professional conference that, you know, whenever you're in a career, go to it, especially if you're feeling like things are really getting you down. I can't necessarily recommend it if you're like in a particularly, you know, profit-oriented business, you know, profit-oriented field, but in my case, because it's academia, like I 100% absolutely love going to the professional conferences because it's just people sharing ideas. We do tend to have like vendors and people coming in who are paying for all of this. We're paying for making sure that we get a space to deal with our feelings about, you know, administration and everything else. But we're not like super, like not all of our sessions are about selling something. And that's really important to me. We need to have sessions where we just talk about cool stuff we've seen, cool stuff we've done. And so Peter Liljedahl did a keynote address when I was at Amatic. I was just about to start pulling out my grading. Yeah. I was just about to pull out my grading and start correcting papers, but given that the keynote was, you know, like 3,000 of my closest friends, it didn't matter. Nobody was going to see me. It didn't, yeah. But within about 30 seconds, I knew I was getting no work done and ended up taking notes the entire time. I reworked my class for Monday, and this was Thursday. And basically for the entire rest of the semester, I attempted to do something like what Peter had said. Sunil Singh did a session. There we go. That's the word. Did a session on like trying to build storytelling back into mathematics. And in his book, he's mostly talking about like intentionally go out there and get yourself lost in mathematics. Just go play. Stop worrying so much about like what you have to do. And the two of them kind of dovetailed together very nicely, even though the two sessions were like a day apart. So I'm taking problems individually from Chasing Rabbits, and Peter suggested in his book that you should have like a few, and now granted this is K-12 and I'm 2-year college, so it's not quite the same population, but whatever, it's close enough. Have a couple of like non-curricular fun little puzzles for people to solve right at the beginning of class. And so this is one of them. I saw it solved by 2 different methods, and I have a third. So kind of all works. Yeah, anyway. So the first one was using trig, and these students went like all out doing law of sines to try to figure out some of the angles that are here, and eventually worked down so that, at least I think some of them did, got that the height of the big triangle here is 2/3 compared to 1/3 for the smaller. Yeah, and so the other thing with Peter's style is that he has data to back it up. Like a lot of data. So he worked with 400 high school students in, I believe, just Canada, and sorry, not students, high school teachers in Canada, and said, nope, wrong again. K-12, 400 K-12 teachers who were willing to change something about what they were doing. And so he came up with he had a few people that he was talking to, and they came up with 6 variables, and they were going to go out there and just change 6 things. But almost immediately they realized that it was just not going to happen with only 6. And so they increased. They all sat down and said, what is it that we care about? Like, what is like the major things that we care about that we need to do in class and out of class? And so it was like, you know, where the students are working, how they're working, how we do assessments, how we do, like, you know, all this stuff, how we form groups, whether or not they're in groups, you know, what are the proper group sizes and all this stuff. And so they identified 14 specific learning tasks that teachers need to think about before doing all this stuff, or while doing all this stuff. And so I implemented like 4 of them immediately. I was able to, without even pausing, I was able to create visibly randomized groups of 3 students, have the students work on vertical non-permanent surfaces, go around, and while I'm like assessing where the students are as groups, intentionally don't answer them anything apart from like keep thinking type questions. So don't give them answers. Ask them something in a way that gets them to think even harder. And there's probably a couple more in there that I forgot, but oh yeah. And the task is given to them early in the class, like within the first 5 minutes, standing and verbal only. And I was like, excuse me? Pretty much everybody was like, no, hang on. You can't tell me that just giving the students a verbal cue as to what they're supposed to be doing was successful. And he said, yes, in fact, it was most successful compared to like all of the different ways that he tried to get it done. It was ridiculous. And in every single case, anytime that they tried to alter what they were doing, so they came up with a list of like institutional norms. So the standardized things that all teachers do, right? The institutional norms. Anytime that they changed any one of those away from the institutional norms, they found that students think more, they think longer, and they succeed more. Any change from the institutional norms gave them progress, improvement. And so they're like, well, so then once they moved away from that, they were like, okay, let's try to do like, 10 different things. What can we do for this one thing? So they tried, randomizing the groups. They tried getting like Canvas to randomize the groups for them. They got the students to pick whatever groups they wanted. You can imagine how that went. They got like, however big you want to make your group, just do it. Do individual, do in groups of 2, in groups of 3, in groups of 4, in groups of 5. Like you're all working together as a class, just mingle, like all of this. And they found that 3 was the magic number. So if you went to 4 or 5, typically one or two students could just kind of slack and just be like, nah, whatever, I'm cool, I don't need to do anything. They got it. In groups of 2, sometimes you got 2 students who did not know how to do it and didn't know how to think about the problem either, and so they got stuck too easily. So 3 was very unlikely to have all 3 students not know what's going on. And then they said, if you just get the students to pick groups themselves, they do terribly, because again, typically you've got one student who knows who like the smart kid is going to be somebody who's just not going to care all that much. So, or the person who's not going to care all that much is going to try to seek out the person who's going to like do all the work for them. So again, they decided, no, this isn't how this is going to work. We're going to do randomizing. So they get the learning management system to randomize. Right, and friends don't necessarily do the work. So they get Canvas to randomize the groups. Or they got the teacher to pick the groups. But the thing was that the students didn't perceive either of those things to be different. Like, they'd see randomized groups and they'd be like, he picked them. Or something like that. And the teacher was like, huh, interesting. You think that I picked, despite the fact that it's random. And so sometimes it was like, well, why did you pair me up with this person? And so it became more of like outsmarting the teacher in terms of like trying to figure out why did they pick this person rather than actually just doing the work. And so they were like, okay, we've got to make it visibly random. And so they went out and they did some sort of method, whatever it was. They open up Canvas and click the randomize groups button in front of the kids so that they could see them doing it. They would take out a deck of cards and then just hand out cards or pick a card, any card, all the way around the whole room. And everybody flips over the card. Okay, well, it was random. You had a free choice to pick whichever card you wanted. So there you go. And in either of those cases, the students did better. Because they weren't trying to like figure out why the teacher picked these groups. No, they just got to it. When students were working like on their, either on portable boards, which they could put it down on their desks or stuff like that, they would be sitting opposite somebody and they'd be looking upside down at the other person's work. And so things went slower. Like, what the hell, man? That was a thing. And so they were like, okay, we've got to get these students like to work on vertical surfaces so that whenever you're writing like this, everybody around you can see exactly the same thing. And so they did that. And then they said, okay, we could do portable boards, I guess. But then, you know, the students are sometimes writing down here and then pulling it up. So they said, we're not going to give them anything. They can just find space. And he said that oftentimes what they did was they just put up like, you know, sheets of laminated, you know, the like just laminated whiteboard, or like lined paper that was just laminated on the wall, and they'd start writing on it almost immediately. Whenever they were given paper, they were like, because they wanted to like put down the work, but at the same time, if they screw up, it's really intimidating. So they didn't want to write down stuff. And I was like, you know what? That's exactly how I feel. Because I've got like 10 of these. Let's see, do I have one? Yeah. I've got 10 of these composition books that I was like, I am totally 100% going to do my like my final notes in here for each of my classes, to say like, you know, here's my master set of notes for differential equations, for example, right? Anytime that I teach differential equations, I'm going to pull this notebook off the wall and I'm going to be able to do it. Okay, I started this in 2016. That's how far I got. 4 pages. Because it's really intimidating to think to yourself, I'm going to write this down and it's going to stay here forever. Even though I've got 150 blank pages, I have $90 worth of these things. And I have used 0.2% of them. Though I will say, now that I've started on this thing, I can actually feel slightly less intimidated about it. Or now that I know that I'm going to feel intimidated, I can like work out a couple of examples ahead of time to really, really solidify it. You know, it's been a little weird, but anyway. Yep. So I actually went out and started lesson planning in the middle of the hallway. Specialty dish. Yep, we're doing all right here. Glad to hear you're doing well. Yeah, so I went to the whiteboard that is outside of the main office, and I just started like writing my lesson plan on the big giant whiteboard. I didn't feel like walking into, you know, a classroom or anything like that, which they were all empty at the time. I didn't care. I probably could have. But being out in the middle, like with the chance of like some of my colleagues walking by, actually felt good because I could like get opinions and stuff like that. So I felt really awesome. I was like, you know, the two people who went with me to this conference walked by, and I was like, see, vertical non-permanent surfaces, man. number of them got the wheelie whiteboards, and those worked all right. A number of them got whiteboard paint that they put on the walls, and those worked great. I walked into my classroom on last Monday when we got there for the first day, and I went, our entire wall, they took off all of the boards. And I was like, but the good news was that they did uh, the whiteboards all work, or the whiteboard markers all work on glass. And so I have been letting them completely vandalize our windows, and they absolutely love it. College students, but still, they're some of them are still high school students. They're just in the um, uh, our accelerated program. Yeah, the whiteboards are so great. I actually bought one at NCTM, National Council for Teachers of Mathematics. Had a conference in 2015 in Philly, I think it was, that I went to, and yeah, I got a blank side and a graphing side. I love it. It's so great. This one's a little dirty, so I need to get some rubbing alcohol and give it a once over, but yeah, I was always like I could do this here and have a whiteboard that I'd be able to project, but I just haven't really used it. I think with the digit hope that wasn't something breaking. Yeah, okay. With the digital whiteboard, it's been doing great. Like all this stuff. The only problem that I have with the online app is that occasionally it starts slowing down a bit when I write a lot. But I absolutely love just the concept of using an online whiteboard. The app has been pretty good, but unfortunately the app is not available on Linux, and I made a complete switch to this is a Linux box. So I just was sick of paying Microsoft. I'm sort of I was kind of a Windows Power user ish, and just decided that I was done with Microsoft. I didn't want to pay them extra $200, whatever. And then I think they're going to a yearly model anyway. So I was just like, yeah, we're not playing this game. Or they will soon. I don't remember what it is. They're talking about it. I'm like, nah, I'm done. So I went with Ubuntu, and I've loved it so far. I've only had a major crash twice, which required me to completely reinstall the entire operating system. So only twice, and it was like right at the beginning. I was starting to worry because I was like, oh no, is this going to become a habit? But nah, it's okay. Dual enrollment, yep. Yes, that is true. Most of our high schoolers in dual enrollment do really well, mostly because they're just super motivated. We've been trying to get a lot of our students in, like, well, I mean, typically overcrowded high schools are the ones that send people to us. They do a couple of, like, shipping around, where students from one overcrowded school will go to one that is slightly less overcrowded, but, like, the parents don't like it too much. First of all, the parents in the receiving school don't like it because their class, average class size increases, and also it's those kids from across the tracks or whatever, You know how they get. It's all NIMBY. Me, I'm like, let's get my kids to, interact with anybody. Anybody. The ultrafine point markers, yeah. So I used to have essentially whiteboard markers that looked like overhead markers, like the wet erase ones. Um, so yeah, I was using those for a while for small stuff, especially on the small board like that. And it's so easy now. You just whip out your phone and take a picture of whatever it is you're doing. And like all of my notes are available for my students. All my notes are available for my students online, usually within a couple hours of class. And this semester, it's almost immediately because I have a break after every single one of my classes. At least an hour. It does also spread out my schedule quite a bit, but it's actually really good. I like it. Okay, so anyway, what they were advocating for in terms of how to teach is you can do I started doing 10 to 15 minutes of review at the beginning of class. What have you been working on since the last class? I'll ask a question like on this one, most of the students did not get this done in the 20-ish, 30 minutes that I gave them to work on this. So we had a bit of review at the beginning where I said, okay, here's what you should have gotten from last class. I'm not going to do this every class, but just letting you know. This is what you should have gotten out of last class. Oh, by the way, when I said your paper homework can consist of two different things, one, I told them that they can take the paper homework as is written in their syllabus. So it's just take two questions that were pre-assigned by the coordinator and do them. But I said you have to go through step by step and be very specific about what it is you're doing. Write a little blurb after every major thing. And I said, any of you who know how to comment code, do that, but it's math homework. What is it that you're doing and why? Not at every step, but every few steps, every major different thing that you're doing. Explain what it is that you're doing. And I said, you're going to do this as if it were somebody who doesn't understand math or understand this level of math. So maybe it's, your boss at a job. Maybe it's your kid or a friend who's trying to learn this particular subject, or somebody who's at in a lower math class but needs help on something, needs help to understand what it is you're talking about, whatever it is. And the other thing you can do is, instead of each of those individual questions, I want you to struggle on doing a harder problem. That's where Sunil Singh comes in. And he said what we need is that students understand that, this is going to be a multi-day process to figure out most of these big problems. So, the big problems need time to ruminate, to ferment in your head, if you will. In order to come up with something interesting, in order to figure it out. So I told them that, for instance, the last thing we were talking about was the physics of integration. So we're looking at, from Calc 1, right at the end, you all talked about acceleration functions. And then acceleration functions will be anti-derived or integrated to become velocity functions, which will be integrated to become position functions. Okay, cool. So what I would want you to do for homework is something like, my first car was a 1988 Plymouth Reliant station wagon. Compare that to a modern car like Tesla 3, let's say. Something that is maybe not comparable, but you can easily find information about it online. So, how much of a head start would the Plymouth Reliant need in order for a quarter-mile drag race to be fair? That's it. That's the only information I'm going to give you. And that's the kind of question that I would want you to struggle with for a few days to try to figure out how to solve it. And I said, now this kind of problem is not, this particular problem is not very difficult, right? You pretty much know how to solve for it. It's not a big deal. All you need, what do you need to do? And they were like, well, find the acceleration for each car. Yep, all right, then what? Well, then you can integrate both of the acceleration equations, get a position equation, and oh, by the way, both of them are starting from 0 velocity, so that's nice and easy. And the position of the station wagon is going to be the only non-zero term in that. Right? The Tesla's going to start from 0, 0. And both of them start at 0 velocity. So, go. So it's going to be a super easy question. But it's just a matter of writing down all of the parameters that you need. Writing down the initial values, things like that. So what they recommended is right at the beginning of class, look at what have you been working on? So what are these other little things? What is it that somebody has figured out from last class? And then have them explain it, have them present. And it shouldn't always be the same people, but sometimes it will be. Right. So problem solving is really going to be the main focus of all of this stuff. It's not just random problems and stuff like that. It's going to be fairly intentional in terms of what it is that individually need to be asked. So what have you been working on since last class? Report on progress. Do a little bit of group work maybe. About 15 to 30 minutes depending on, what kind of problem you have, how long it is, all that good stuff. Work on warm-up. Now we have a long time in our class. We have an hour and 20 minutes. Nope, hang on. What am I doing? I go from 10 to 11:45. So I have an hour and 45 minutes. Twice a week. Other people might have an hour 23 times a week. That's not right, is it? Yeah. I think some of our classes we're getting away from 3 times a week just because it's a lot of credit hours. All right. So this is non-curricular. So Peter Liljedahl suggested, for instance, card tricks, right? Not sleight of hand card tricks, the math card tricks, the ones where you end up laying out, 9 cards, and then saying what column is it in, and then laying out another 9 cards, what row is it in, and then you're able to just count out the number of cards and flip over, is this your card? Or doing the, yes, combinatorics, or doing the ternary. Oh, no, that is it. It's ternary. That's the one. So you count out which row is it in, which column is it in, and it gives you an encoded position in ternary as far as what position the card's in. So you can jump back in, flip out that many cards, and then flip over the last one and say that's your card. And people will be like, how'd that happen? And then that's where you go, figure it out. Right? Go. here, this is where you go 60 to some odd minutes with curricular activity. Once they're warmed up, they're more likely to think, and again, think longer about whatever activity it is you've got going. Once they've gotten a little warm-up from the non-curricular puzzles and activities, they're more interested, they're more invested in doing something that might be hard. They're more invested in thinking about something. So you pull out the curricular activity. Today for my class, it was looking at U substitution. So I went around and I just said, okay, you know, everybody's going to work on this one. This is the integral of parentheses x plus 1 to the 4th dx. Go. All right, everybody got it within like 10 minutes. Some of the other groups were screwing around a little bit more, so they were like unable to figure out exactly how to make it work, and they didn't talk with the other groups around them, which is something that, you know, we need to work on. But then I turned to like one of the other groups over here, and you know, they were done in a matter of 2 minutes maybe. So I was like, okay, here's another one, and throw it to them, and it's harder. And so it's like, you know, a U substitution involving sine or cosine, or one of the other groups was like, you know, 1 minus x squared with an x on the outside raised to a power over here. So how do you integrate this? And again, it's just simple U substitution, but you know, the ones who figured it out, oh, this is the exact same thing, like they just did it. There were a couple of groups that got tripped up because in the original one, dx and du were identical, and so, right, who cares? It's just a one-for-one trade. But now I was giving them something where dx and du had to have a constant trade, right? You had to introduce a constant in some way, shape, or form. And then they were all like, how do you manage this? A few of them sort of knew how to do it anyway, and so they just kind of like helped their group through. Then we came back after a while and said, like, you know, let's go around the room. All of you, you know, these groups over here got an extra problem because they were just working fast, you know, and I did not call attention to the 2 groups who kind of were a bit slower getting in, obviously. But, you know, they could feel it. Which is a little too bad, but you know, it happens. So I said, all right, so how's this working for you all? And they were all like, oh, this is, you know, kind of, it's working, I think. I got one guy who is like, I don't learn this way. I learn by like you standing at the board and telling me how to do something, and I'm like, yeah, that's not happening. That's not happening this semester. Like, I'm very sorry, but so I sent Peter a message on Twitter. I was just like, so hey, how do you deal with students who are like this? Or maybe students who have like, you know, are on neurodivergence or various other spectra. And I haven't gotten an answer back yet, but, you know, just kind of like, do you have this, or was there a guaranteed, I mean, not guaranteed, but, you know, in all of what you did, is everybody across the board improving? Or is it like, you know, 99% of the people are improving and the other 1% are a very specific demographic group? Because I'd like to know that. I'd like to know whether it's in this guy's best interest to transfer out. I don't think so. I think that it is going to be in his best interest to stay, because he also needs to break out of that habit of just like focusing on this is a like thing that I need to rote memorize. I told the class a bit about this toward the end as well, and I was like, you know, the way that this is going to work from here on out, and not just me, but like Calc 2 and up, is that this is no longer going to be a prescriptive, here's your question, here is the way to get it done. And it never really was anyway. But, you know, we get into this mentality, teachers too, we get into this mentality of here's the way to solve this problem. And on day one, I walked into class with a yeah. Right, and I think that he's just locked into this way where he's just like, no, I'm not doing anything different. I'm gonna do this, whether or not he's on the spectrum or whatever. It, you know, I don't know. Anyway, but yeah, it was I was yeah, and he was really the only one who was like really vocal about it. Everybody else you could kind of tell was like, I don't know, but I shared with them like all of the major points that they went through in talking about Peter's research. Like, what was it that happened in all of these steps? Oh, would you look at that? Like, almost every single thing is doing better. Like, every single person was doing better. And also, the student behaviors that came out in this study. So Peter said that generally speaking, there were 5 student behaviors that existed within any of these activities. So group 1 was like out of a typical class of 32, I think it was, 6 fell into this group of 6. A fair number fell into this group of slacking, which is that they just didn't want to do the work. They didn't know or didn't care what was going on. All right, give me 1 second here. Okay. So in a typical class of 32, they had somewhere around, maybe this was a smaller group. I think it may have been 2, who fell into the group which they identified them as slacking. So they didn't know or didn't care what was going on. Everything was just like, whatever. Nothing matters. I'm only here because I have to be. That sort of thing. Then they had a group of 6 that fell into the group of stallers, who basically like just were going to do stuff that was kind of off task. So they weren't on their phones, because like that is slacking. but they were like looking in their notebook or looking for a pencil or trying to sharpen their pencil, go to the bathroom, like get drinks of water, all this stuff. So it's off-task behavior, but legitimate at least, that was under the air of like, I just need to get something else done before, I actually get to work. And so this group was interviewed, and they said in their interviews that they knew that it didn't really matter. The teacher was just going to go over it anyway, or whatever. So they didn't have to do the work themselves. Just why bother thinking, basically. The next group was, let's see, slackers, stallers. I'm going to need the book again to remind myself what they are, but so this next group was people who were essentially stalling but using on-task behavior. So they were like thinking up in the air, talking with their friend about math, but not necessarily this problem or how to do it. Just kind of like, because again, in interviews, they were basically the same as stallers, but they were pretending that they were doing the work. Pretending. Fakers. There we go. Another 6 or 7 were considered fakers because they would try to look like they were doing the work, but not actually do any work. So again, legitimate on-task behavior. They're thinking about it, just, tapping their pencil to the paper, making some notes about it, but again, really it wasn't that. Then almost half the class, 17 or so students, and I told them I was called out really hard by this book, talking about this particular group. Maybe. Or they were just like, or the stallers, like the split between fakers and stallers, could be either less confident in material, or it could be that like they just hadn't gotten to, like, they don't need to pretend that they're doing the work. They just find something else to do. And they know how to manipulate the system that way or what have you. So half of the class, 17 of 32, were considered mimickers. And these are students who look at the problem on the board that was all done out for them, look at the problem on the paper, and then try to match one for one exactly the process that was done along the whole thing. And I went, holy shit. That was me. Yep, that was me all through high school and good part of college too. It was only when I got to differential equations and then a couple of my junior level classes that I went, wow, I cannot do this anymore. This is not going to be a successful strategy. Like, I recognized it. I was like, no, no more, can't do it. So I actually had to like go back a little bit and retread some of the math that I was doing, because just mimicking what was being done was no longer going to work. Now, I had been a smart mimicker in that I could go back, look at what they did in the book, and also go a few steps further, where it was like, well, if I have a tenuous grasp of what to do between here and here, I can do it. It'll be fine. I'll try it. I'll fail. I'll try a few different ways around here, but it's almost identical to what was in the book as the example. So I'm good. I was totally called out. I'm like, oh, oh, wow. Okay. And he said in interviews, the teachers had said emphatically that they did not want their students to mimic anything that they were doing. And he said, ironically, 100% of the mimickers in the class thought that mimicking was the exact appropriate behavior that the teacher wanted. What do you mean I'm not supposed to just copy exactly what they did on the board? So, and then the last group, the rest of the 6 students or whatever, were considered the just try it group. And so what they do is they would go through, they'd maybe take a look at the example on the board, but more importantly, they just got into the problem and started deconstructing it and being able to throw stuff around and being like, well, this thing doesn't work, so let's try this over here. And they would just do stuff and manipulate things and try things that were beyond their exact ability of what they've been shown to do. So they were just trying stuff. So just try it. And so that group was also asking interesting and thoughtful questions of the teacher. The teacher was giving them feedback, and they were going back and forth, stuff like that. And that was the intended route for this particular class. Again, none of the mimickers were realizing that that was the intended path. Yeah, so like I said, I got called out hard. So the first group here in this problem, again, find the area of the black triangle here. The first group used trig. Most of them use law of sines in order to figure this out. A bunch of them attempted to make these right angles. And I was like, how is that going to be a right angle? Like, where would this have to be? And they're like, oh, I get it. This corner here would have to be in that corner there. It wouldn't be at the midpoint. It'd be at the other corner. I'm like, okay, there you go. And so there was a lot of questioning as far as what was going on with all of these individual. We had some really good thinking and really good questions that were being asked. And they kind of got it in terms of I'm not going to give you the answer. Finally, they kind of got it. I was just like, no. That's, they'd ask me a question and I'm like, just stand there like, And then one of the other people at their group would be like, oh, no, it doesn't work. Like, huh, okay. And just walk on. So then a second group tried to take the calculus, calculus 1 perspective, where somebody said, wait. No, I got it. This is what we're doing. This is only 1 or 2 groups. They said, okay, this is a right angle here. This is going to go, let's call this 0, 0. Let's call this 0, 1, and this 1, 0. So therefore, the area we need to find here is this triangle. We have no idea where this location is, but we do know that the line that this is going to create here, the line that is going to define this point here is going to be 1/2, 1, and 0, 0, and 1/2, 1 are going to create this line which is y equals 2x. Okay, and then this line over here is going to be y equals 1 minus x. So where do these two things intersect? Well, that's easy. It's a linear question, right? It's a linear problem. So where are these things going to meet? Well, this is y, this is y. So 1 minus x is going to be equal to x. So add x to both sides. You got 3x equals 1. X is going to equal 1/3. All right, cool. So then the y value for this is going to be 1 minus 1/3 or 2 times 1/3. Either way, it's going to get you 2/3. So 1/3 comma 2/3. And then he went and said, all right, so the left triangle here is going to be the area from 0, x equals 0 to x equals 1/3. I was like, really? Of 2x dx. Plus the area of the right triangle is going to be from 1/3 to 1 of 1 minus x dx. And I just was sitting back, I'm like, fascinating. I never thought you'd be like so into doing calc and taking this particular thing. Yep. In fact, I'm not even sure that he found the y value. I'm not even sure he found the y value. He may have just found the x value because he was so focused on I need the x value to figure out where the break in the integration is. That I think that may have been what happened, so that he didn't actually find that. Where he just said, let's do this. So this is going to be x squared evaluated from 0 to 1/3 plus x minus 1/2 x squared evaluated from 1/3 to 1. So here this is going to be 1/9 plus here the ones are going to make 1 minus 1/2. So that's going to be 1/2 minus 1/3 is going to be 1/3 plus 1/2 of 1/9 is going to be 1/18. Right, so then let's make sure I actually did this right. It's going to be 2/18. 3/18 is going to make 1/6. And then 1/2 minus 1/3 is going to be also 1/6. So we get 2/6 or 1/3 for our area. Now I don't know what happened. He got caught somewhere in here where something went wrong. I think it was probably just a minus somewhere, but you know, for whatever reason, I couldn't quite parse exactly where he went wrong. I also did not know the area ahead of time. Like I knew how to find it, and I knew that the height was 2/3. But I screwed up in that I just somehow forgot to find the area, I think. I was just so concerned with I was concerned with just finding the height of this that, yeah, just completely went off the rails. All right, and the way that I did it was I said, oh look, vertical angles. Oh look, 45 degree angles, which make opposite interior angles. So by angle, these are now similar. So 1/2 is to 1 as height here is to height here. So h1 is to h2. So h1 plus h2 is going to be equal to 1. And also the relationship that height 1 is half of height 2. Or 2h1 is equal to h2. So then I was able to say, okay, that's going to just be 3h2. No, okay. 3h1 equals 1. There we go. Jeez. I'm okay, I promise. 3h1 equals 1. h1 equals a third. h2 equals 2/3. And therefore area is 1/2 base times the height. So half of 2/3 is giving us a third. So once we get a few more students who show how they did it, and see if there's anybody other than these two groups in terms of how they got the answer, then I'm gonna show them mine and just say, like, this is, all of these are valid, right? Every single one of these is valid. But we have the geometric method, we have the calculus method, or this is also geometric, it's just found through an algebraic window. And then here we have trig. So like all of them work, and all of them will get to the same place. And if you know how to do all three of them, and there are more out there that we probably don't even know about, the more different perspectives you get on this, the more rich your understanding of how this all works is. Because and this is another thing about Calc 2, is that oftentimes there is not one way to do something. You're going to find that there are multiple ways to do things, and all of them are right. So go find stuff, right? That's what really Sunil Singh is getting into in his book. And if you have it in your library, go for it. If you don't, maybe request it. And if you feel like buying it, definitely buy a copy, because it's worthwhile. At least if you're into like math education at all. Right? It's good as popular reading, but it's awesome as reading for teachers. That's to anybody. So anyway, this is what Sunil is getting into in this. His whole idea of this chasing rabbits thing is you're supposed to go and get yourself lost, just like Alice through, Alice not through the looking glass, but Alice falling down the rabbit hole and going into Wonderland, right? You have this sense of awe and wonder which pops up all the time, and I mean, you see that in Dodgson's work as well, aka Lewis Carroll, right? He has this sense of awe and wonder at the entire world that he's trying to convey to Alice. Not just Alice in the book. Alice, his advisor's daughter, whom perhaps there was a controversial affair, but we won't talk about that. So, so he was writing this book not just about this girl Alice, but he was writing it to Alice, the girl that he knew, right? That he was trying to get her to see the wonder and awe that existed within mathematics. He was also trying to make fun of a bit some of the established mathematics of the time, which was also starting to get into like set theory and other crazy stuff, including imaginary numbers that he saw no use for whatsoever. And then we had all sorts of ideas like transfinite numbers, which oh, that must have been after. No, I think that was well after his time. But there were sort of other workings that were like that. Let's see, what did he work on? Or what did he... I can't remember what else it was, but yeah, Charles Dodson was not very happy with some of the new math that was coming out in the academia, in the academic world. Yeah, he was just not having it. So he wrote some of his... He was writing some of his work in order to sort of make fun of and poke fun at some of the other math and mathematicians that were going on about these crazy ideas that nobody was going to ever use. Didn't make any sense. Don't know why anybody would ever use that. It's so bizarre. Yep. Yeah, there was... You probably don't want to look up stuff about him and Alice. It was a little creepy, but overall, yeah, he was really pissed off about some things. I think he felt at some point when he was probably about my age, honestly, he felt that like his contributions to math were kind of coming to a close because it was getting so far beyond him that he was just kind of getting upset with it. Anyway. Mm-hmm. Yeah. And I've been delving recently into mathematical history in order to try to give credit where credit is due, because there are a lot of places where like the where the Eurasian world is really given a lot more credit than probably is owed. And kind of like how, Newton is responsible for calculus, like that negates so much in the entire world of mathematics. It wasn't just Newton. Like, even during his time, it wasn't just Newton. Yeah, sure, he was the one who came up with the prevailing notation used in England. He was the one who came up with certain ideas probably first. But the idea of a limit, the idea of taking smaller and smaller chunks of time, that dates back to Zeno in Europe. That's like, 500 BCE. That dates back to probably around the same time in China. That dates back to around the same time in India, maybe even earlier, because India did not have the same hang-ups as anybody else. India, the mathematicians there were able to think about infinitesimals and infinities very easily. It fit their philosophy. In a lot of the other areas of the world, infinity and infinitesimals really didn't fit their philosophy. And so because it didn't fit their philosophy, they just never really thought about it. It didn't make any sense. Why are you thinking about such imaginary numbers? Yeah? Mathematical physics. Yeah, I have several books in my basement right now on mathematical physics from the 1950s through the 1990s. I have inherited 9 boxes of books, and I was not expecting 9 boxes. So a friend of ours was moving his father out of his house finally, and moving him into assisted living. And he said, "All right, Dad, what do you want done with this?" And he was just like, "I don't know." It's, all of his books that he collected as a math teacher at a university. And so he said, I've got a few friends who might be interested. Is it all right if I just give them away? And he's like, "Nah, it's fine." So I was fortunate enough to say yes, and I've taken the last, I've taken a couple hours once or twice a week in order to try to catalog the books. I have somewhere around 50 books probably cataloged at the moment, and I'm 3 boxes in. So we're looking on the order of 150 to 200 books. So I'm gonna find a few people, I think, who really want some of these things. Yeah, it is. There is a book in there that was written by one John von Neumann. There were a number of books that were written by people I have no idea who they were, and I'm kind of interested in looking them up and trying to figure out who they were. In a lot of cases, they were just a professor of mathematics at Yale or Caltech or something like that. There's a lot of, as you would expect, Dover books. But a lot of the Dover books are also reprints of lectures given in Germany or France or somewhere completely different. So in the 1950s, nobody had access to these particular lectures, and also, even if you did have access to it, it was in its native language. So, you might not know, you might not be able to get a transcript of it. So Dover publishers decided to translate all of these books, or translate all of these lectures and put them into books. So yeah, I'm gonna go through the entire catalog and figure out if he has anything that's worth, several $100s just by itself, and give them right back to him and say, "You want to sell that." But he was like, "I very much doubt that he has any of those." I'm like, "I don't know." He's a friend, right? It's not like it was just some random guy, right? I know how to contact him. He's a friend. If it showed up on eBay for $300, he might be kind of interested and go, "Huh, well." I mean, if it was a random person, I might take the proceeds and then say "Oh, by the way, if you want, here's a cut." And it might not be half, and they might be like, "Oh, huh, just out of nowhere, I have money, extra money, cool." That's a thing with me. I don't know. It doesn't hurt to show a little extra goodwill. And that wouldn't necessarily be goodwill, because I'd still be, in that particular scenario, that's still kind of taking advantage. But yeah, I try. And I think it was really I mean, both my parents, but, my dad especially, just always seemed to know just the right thing to do. And he tried to really push that into both me and my brother. But, I mean, even just recently with Sunil Singh, this was not, like, this isn't exactly the same, but it was something that kind of resonated with me because I do it anyway. I can't remember the exact quote, but it's not your ability to wait. It's your attitude while you wait. So especially recently, I just don't care about like a lot of things that are going on in terms of like I don't mean like, politically or whatever. I'm very charged about a lot of stuff, but for instance, like somebody was taking a really long time in front of me in like groceries or waiting for an order in a coffee shop or something like that. I didn't really have anywhere to be, right? Like, I can afford to wait. It's fine. I just don't care. It's fine. And the lady turned to me and she's like, I'm so sorry. I'm like, it's fine. Don't worry about it. You're good. And I think that Sunil was talking specifically about like problem solving. It's important to have downtime where you're just waiting for the answer to kind of come to you. Where you're just thinking about nothing in particular, or you're thinking about the problem, or you're not. It doesn't really matter. Eventually you're going to figure it out. But if you've got this attitude like, I've got to get it done, then it's probably just not going to happen. You can always work at it, and maybe it will. It could be just a matter of hard work. That's always a possibility. But in a lot of cases, it's a matter of just taking some time and relaxing for a bit. Let it flow. Let the subconscious section of your brain work at it for a bit and see if that just kind of does it for you. Go do something else for a while, come back to it and be like, huh, that's super easy. And then just write it down. Oh, there's a completely different way that I'm looking at it now. Like, would you be doing the, blue or red method here, and then finally see the green one and just be like, oh, those are similar triangles. Right? Like, is that where you get it? Is that where it kind of unlocks for you? Is that whatever it might be? So, like I said, recently, probably 10 years ago, I was working in the student lab, and I'm just like, I kind of get impatient with some students, and they're just not seeing it. Like, they're not seeing the thing that I've got in my head. And it's just the complete wrong attitude to have. So if you, just sit back a ways and let whatever it is happen. Like, I wasn't going anywhere. I was in the student lab. I was gonna be there anyway for an hour. What am I so stressed about? So like that's been my attitude for at least the last few years. And it was even before the pandemic, but especially since. I've just been calming down a lot. Maybe that's a function of hitting 40 or whatever. But yeah, like just we all have to change our attitude and understand that no, it's cool. Like just relax, it's fine. So yeah, Liljedahl and Singh were both instrumental in making this change in me. Not that particular change, but in making this curricular change for me. In saying like, let's make sure that we're actually serving all of our students to the best of our ability, and let's get some numbers behind it. So between, again, Peter and Sunil's books, I'm really liking what they're doing. Sunil's book, Chasing Rabbits, I got probably about to the midpoint, and then I stuck my pencil in there and I started going back and tabbing all of the pages that I had dog-eared before, and like underlined passages and stuff like that, and wrote on the tab. This is the first time that I've ever actually tabbed a book. Like, really? I'm just realizing how awesome it is, and why didn't I do this before? But yeah, especially like my textbooks. I could have been tabbing my textbooks in college. So I've been keeping up a fairly regular posting of these two guys' stuff on Twitter, and then also just been like constantly like tagging one or both of them in posts and just being like, hey, what about this? No, it's fine. That's what I'm here for, really. I mean, you know, answering math questions is great, and anybody can post math questions in the chat, and I'm perfectly happy to do them. And you know, if it's going to be like specifically math, then you know, we've got all these different things that we were doing. We were doing trig substitutions. We were doing, you know, statistics down here. So yeah, there's all sorts of stuff we do. But yeah, anytime you want to drop in, anytime you want to throw something in the chat, ask questions, feel free. We'll be around. And I'm here on Tuesdays for math and Fridays for games. So see you later. Have fun. And if anybody else is feeling like dropping in a question on mathy type stuff, let me know. And if not, we're going to probably start looking for a friend. See who else is on tonight. Heyo! Welcome and thank you for the follow. If you have any questions about math or education in general or anything like that, let me know, and I'll be happy to answer. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We do math here on Tuesday nights, and we do gaming on Fridays. Lately, I've been getting back into Astroneer. It is a survival, spacey type game where you run around and build a base and do all sorts of cool stuff. Alright, I think it is getting to be about that time. So, since nobody else has dropped any particular questions in the chat, we're going to rate out to, let's see. We got Boss Lady B doing Elite Dangerous. We got Aaron Stevie doing Crisis Core. H-Ray doing Red Dead Redemption. The Gigglepuss Gang, who, I will say, most of the rest of the people are fairly on the, like, mature streamed kind of things. Gigglepuss Gang, oh man, that is definitely 18 plus. They're doing Valheim. Yeah, all right. Let's go see Gigglepuss Gang. Again, this is a mature stream. They are extremely unafraid of literally anything. So, be nice. So it looks like they are working in the swamplands at the moment. Alright, so we're going to rate out. This is going to be about 10 seconds here. So, I hope you all have a good rest of your week. This has been a very good start to mine, and I hope you all have a great time. So, with that being said, I will see hopefully everybody on, Friday. We're doing some Astroneer, and I said we're possibly also going to split the stream and go with Final Fantasy VII Remake. I do want to get back into it so that I can actually finish. We're getting pretty close to the Shinra building section, so I'm looking forward to it. There's also all sorts of crazy new stuff going on. I love it. All right, have a good week. This is Obi-Wan. All right, yeah, and we'll be back next Tuesday for math stuff. So see y'all later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.